Bismillahirrahmanirrahim. I hope that you are doing well with your exam. This is actually an exercise which is basically a theorem which deals with continuous function and uniformly continuous function. So let us suppose that we have a function, real function f, which is defined from AB, which is a closed interval in R, part of R, into R, and we suppose that it is continuous. So if the domain of definition is a closed interval, and if it is continuous, then it is uniformly continuous. How we can prove this? Let us try and start. Solution. By contrapositive, we suppose that f isn't uniformly continuous. This means that there exists epsilon greater than 0, such that for all delta positive and for all x and y from A, B, such that there exists x and y from A, B, such that x minus y is less than or equal delta, and the difference between f of x and f of y is greater than epsilon. Here we can take less than or equal. This is the negation of the fact that f is uniformly continuous by contrapositive. So we suppose that it is not true. And here, remark that delta is a positive real number. For all positive real number, this is true. We can find x and y. For each delta, let delta be equal to 1 over n, and n belongs to the natural number, which start from 1, 2, 3, and so on. For delta equal 1, we will find x1, y1. Delta equal n equal 2, for delta equal 1 over 2, we will find x2, y2. N equal 3, we will find x3, y3, and so on. Actually, here, we can find two sequences, xn and y1. These two sequences belongs to AB, such that what? Such that xn minus yn is less than or equal to 1 over n, and f of x minus f of y is greater than epsilon. Remark that xn belongs to to AB. Xn belongs to AB and Yn belongs to AB. So Xn and Yn are bounded. If they are bounded, this means that we can find subsequences from Xn and Yn such that these two subsequences converge in E using the Bolzano-Weierstrass theorem. By the use of Bolzano-Weierstrass theorem, there exists X phi of n, which is a subsequences X phi of n, a subsequence of Xn, which converges towards let us say x, and x belongs to AB, to x0, and x0, let us say L, it will be more nice, towards L, and L belongs to AB. Why? Because Xn, which is the sequence, is in a closed interval, and a closed interval actually is a closed set. So the limit belongs to this set. And what we have else? We have that if we consider this once again, we will get that X phi of n minus Y phi of n, this is less than or equal to 1 phi of n. And the definition of the subsequences needs that phi of n is greater than or equal to n. So in this case, it is less than or equal to n. And by the way, this converges to 0. This means that they have the same limit. We have here two subsequences from the same closed interval, and they have the same limit since we have this. This means that we can do it quickly like this. Then we can also use characterization for the sequences and the limit, and we prove that it converges to the same limit. Anyway, X phi n converge to n, and Y phi of n converge, the subsequences converge to the same limit. What we have here, we have from a side, f is supposed to be continuous. So f of x of phi of n minus f of y of phi of n, absolute value, this is greater than epsilon. There exists an epsilon which is strictly greater than 0. This is from a side. From another side, this converges to the same limit. So they have the same limit. And in this sense, f is supposed, we have two sequences which converge to two subsequences. We can call them sequences. We have two elements which converge to the same limit, but the image by f of the first and the second converge to two different limits. This means that actually f is not continuous. This is a contradiction with the hypothesis that it is continuous. So if it is continuous on a closed interval. This means that it is uniformly continuous. How we can use this theorem to solve exercise? Next in this video, I will propose for you some exercise that will be solved by this technique. Let us take, for example, f of x. We consider this 1 over x. If we take f of x is equal to 1 over x. For example, we can take f of x equal to x squared. This function, actually, it is not uniform. It is continuous, but it is not uniformly continuous. If we consider f of x, this is not uniformly continuous. If we consider f of x equal to x squared, defined on -1, 1, for example. How can we say about this function defined on this interval? Actually, we can take f of x, which is equal to x squared, and we take -1, 1, which is a closed interval. Then we can say, using this theorem, we can say that f of x, which is equal to x squared, is uniformly continuous on this interval. Why? Because we have a continuous function on a closed interval, and since f of x, which is equal to x squared, is uniformly continuous on this interval, f is actually uniformly continuous on all subset of a subinterval of -1, 1. I mean, it is uniformly continuous on subinterval, especially in particular this subinterval. So it is continuous on this subinterval. Let us move to a more interesting example. How about this function? F of x, which is equal to sine x over x, and x belongs to 2 pi and strictly greater than 0. How about this function? Here, unfortunately, we have a continuous function on an open interval. If we can make it a closed interval and bounded, this will give us the right to say that this function is uniformly continuous. Let us take this function. It is equal to sine x over x if x is less than or equal to 2 pi. We have no problem with 2 pi. It's actually equal to 0. And by extended method, it is equal to 1 if x is equal to 0. This function f tilde is defined on the closed interval, which is 0 to pi. And this function is actually continuous. So we have a continuous function defined on a closed interval, so it is uniformly continuous, and then sine x over x is uniformly continuous on this interval. So we take this function, we put it in a more global function which is continuous with a closed and bounded interval. We answer the question using this theorem, then we will be back to our first form of the function which we discuss the uniform continuity. Another example, how about h of x, which is equal to 1 over x if x is less than or equal 1 and strictly greater than 0.1. Here, in a very easy way, we can consider greater than or equal and take the closed and bounded interval. This function is continuous on this bounded and closed interval, then it is uniformly continuous. If it is uniformly continuous on this closed and bounded interval, it will be actually uniformly continuous on this interval, which is not closed necessarily on the left side. The last example that we will not be able to use this theorem. How about h of x, which is equal to ln x, and x is less than 1 and strictly greater than 0. In this case, we can consider less than or equal 1, we have no problem, but we cannot take x equal to 0. We cannot make an extended function which is well defined and continuous on the closed interval. So we guess that this function, it is not uniformly continuous. Let us deal with the negation of the uniform continuity of this function. This is not uniformly continuous. Why? Because we can find epsilon, which is equal, for example, 1, such that for all delta which is positive, we can find x, which is equal to 1 over n, and y, which is equal to 1 over 4n. Both of them belongs to 0, 1. We can take it closer. Both of them belong to this interval. They verify x minus y. This is equal to 3 over 4. So 3 over 4 times 1 over n. All of them is positive, so we can take off the absolute value, and this is less than delta. Here we use the Archimedean property of R. So for all n, we can find, for all given number, we can find the n such that it is greater. We take this here and we keep this from this side. This is positive, so it will fit very well. It's okay. And what we have, the difference, the ln x minus ln y. This is equal to ln 1 over n. So we have ln 4n over n, which is equal to ln 4, which is equal to 2 ln 2, and this is clearly greater than 1. This means that it is not uniformly continuous. Just the last one, on which I will use the definition of the uniform continuity. Let f of x equal to x squared, and the domain that we will take is x less than or equal 1, greater than or equal 0. In this case, we know that this is actually a very nice, here let us take 4 minus x power 3 for example. This is a continuous function on a closed interval, so it is uniformly continuous. But how we can show that this is uniformly continuous? Using the characterization, I mean epsilon delta. To show this, for all epsilon greater than 0, can we find delta which is greater than 0 such that for all x and y from in 0, 1 closer, which verify x minus y less than or equal to delta, this implies that f of x minus f of y is less than or equal to epsilon. As it is customary, we will start by this since it is a sufficient condition, the existence of delta. In this case, f of x minus f of y will be x squared over 4 minus x power 3 minus y power 3 over 4 minus y power 3. We can simplify, we can get directly, but I prefer the details for my students. In this case, we will get here 4x squared minus x squared y power 3 from this side minus 4y, sorry, here we have 2 power 2 minus, so plus x power 3 y power 2 divided by 4 minus x power 3 4 minus y power 3. This is equal to what we have. We have from this side, so we can take 4x squared minus y squared from this one and with this one, plus x squared y squared times, from this side we have x and from this side we have y, okay, over 4x power 4 minus x power 3 times 4 minus y power 3. We need x minus y, and this is less than or equal. Here we have x squared minus x squared minus y squared, x squared minus y squared. This is equal to x minus y power x plus y. X and y are positive, so it's okay. This is less than or equal to 4x plus y plus x squared y squared, absolute value, only absolute value of this, which is 4 minus x 3 times 4 minus y 3. We can keep the same absolute value, it's the same thing. Times here we have as a common factor, we have x minus y, which is less than or equal. Actually here it is equal, since they are all of them are positive. So we have to maximize this. The maximum of this is for x and y equal to 1. So we get 2 plus 1, 9, over the minimum of the denominator is for x equal to equal to 1. So here we have 3 and here we have 3. So 9. It's a coincidence. X minus y. X minus y. In this case, it is sufficient. So it is not very beautiful. It is not very beautiful. It's the same, but I prefer taking two to have a different result, more beautiful than. So here we have 2 plus 2. This makes 4. 4 times 4, 16, plus the maximum 4, 16. So we have 20. We have 32. And here the maximum the maximum, I mean the minimum, if we will get a problem, because it will be I will get problem. So it's okay for one. Yeah, this is unfortunately this is not the good example, but imagine that this is a real number, which is not equal to necessarily with, imagine that is different of y. Imagine here it is equal to 1. It is sufficient to take this is less than or equal to epsilon. If we take it less than or equal to epsilon, it is less than or equal to epsilon. So the delta that we are supposed to find, the delta will be epsilon over the real number, which is here is equal to 1. But in real life is not supposed to be equal to 1. So we find delta which depends only on epsilon and not on x0, the point on which we are discussing the classical continuity of function. But don't forget that x is less than 1. So x and y, they are between 0 and 1, and the difference here, the difference between x and y can be less than 2. So if you think that it is more interesting to mention this, you can take delta equal to the minimum between what you find here and what they gave you. In this case, this will the difference will be equal to 2. This finishes this video. Thank you very much. See you next time, inshallah.